All right, just to recap, we're talking about nebular theory, where the materials in the center of the solar system eventually gravity pulled them together. Then they started to spin, and as they began to spin, then they clumped together. Higher temperatures and higher gravity in the center, leading to the proto-sun or the eventual formation of the sun, and then the higher temperatures leading the rocky planets, and then farther out you have the made of materials that are less or have a lower boiling point are the gaseous planets. All right, although in some cases they're very big. All right, we started talking about the sun, talked about sunspots that are on it. Basically, the sunspots, again, real quick, are caused by changes in magnetic field. And part of that's because as the sun spins, it also spins fairly slowly, but it spins. And since it is um, more liquidy, plasmy kind of stuff, it rotates at different speeds. It rotates a lot faster at the equator, say, than it would at the tops or the poles, I guess. It's not really called the poles, but anyhow. And because of that, you get these warps in the magnetic field, and that's what these sunspots are. And you see sometimes in clusters. Sometimes they disappear, they go on the other side, but then sometimes they come and go as the magnetic fields get twisted and warped and back and so forth. Okay, some people try to tie them to temperature changes. They do tend to peak in about an 11-year cycle, I believe, where you get more and then you get less. Some people use tried droughts to that, and there's been some correlations, but not 100% proved about that. All right, but anyhow, that's that. Now, um, we talked about the photosphere, which is technically the surface of the sun, and that's where the sunspots are. I'm sorry. We'd already talked about the core on the inside. All right, chromosphere. Chromosphere is a transparent layer. Okay, it's about 10,000 kilometer shell, and it is hotter because all this heat coming from the inside coming out there is very hot. And it is about, give or take, 10,000 K or Kelvin again. And generally, once again, this is only seen. This layer is usually only seen during solar eclipses. I believe it's this layer here. It's the pink layer, but I'll be honest, being colorblind, I have a hard time telling that. Okay. Now, on the very outside, we have the corona, and this is what makes all the neat pictures during the solar eclipse like we just recently had. Uh, it is some of these streams that go off are several million kilometers, so these are extremely wide going off. We don't usually see them, like I said, unless the sun is totally, the rest of the brightness of the sun is totally blocked out. And so, very high temperature plasmas that are moving out, the solar winds, when they send out very powerful X-rays and other high radiation, high power generation. Um, about a million kilometers Kelvin, so it's extremely hot coming off. These give off dangerous things to us, and it is fortunately blocked by our outer layers of our atmosphere. But when it hits the ionosphere, which is that layer up there where we have a lot of ions, that oxygen and nitrogens that have been stripped of all their electrons and so forth. This interacts with that and that helps block it, but that also creates the northern lights that we see here on Earth. Okay, and basically the solar wind is generated. You have these streams of electrons and protons are just flowing out from all this fusion going on in there and stuff. There's ripping off electrons and protons. So they're just streams of protons and electrons that are flying out from the corona. Okay, and that's why it was very impressive. But normally you can't see that because the sun is so bright it covers that up. All right, so basically we've got the sun. All right, the sun is what the whole we said. Think the world revolves around you. Well, the solar system revolves around the sun. Okay, not you or your sister or your brother, whoever else you may know who thinks everything revolves around them. All right, so going from the sun, next we have Mercury. All right. Mercury is very similar in size and appearance to our moon. Okay. It looks like that. It has a lot of pitted craters you can see and stuff like that. Okay. And part of this is because it has no atmosphere, therefore there is no wind, but it also means there's no protection from meteorites and so forth. That's why you see the impact for things have hit on it and stuff, just like the moon, no atmosphere. Therefore, there's no air resistance as the meteorites come through, and therefore they don't heat up and burn up. Therefore, they just go hit the surface. Okay. Um, Very often it's called, often shows up as a morning or evening star. Generally in the fall, September, October, it comes up in the morning. Evening star in March, April, in the spring more. So because and we'll talk about Venus also, but Venus and Mercury are so close to the sun that we tend to see them either right before or right after the sun rises or sets. Okay, and that's why they have this reputation. And so basically, Mercury is either seen, like I said, either in the morning or in the fall or in the evening in the spring. Okay, just for the record, it has a year is 88 days. Okay, um, however, there are only 3 days every 2 years, so it doesn't spin very often. So the days are long, and therefore get very, very hot, and the cold side gets very, very cold. Daytime temperature may get up to 430 degrees Celsius. Keep in mind, we only get up to about 30 here. Is up in the 30 something, is up 35, 36 is up in the 90s. So very, very hot. The nighttime, since they only have 3 days per year, of course, their year is only 88 days, so divide 88 by 3, it's by 11 days, I guess. I mean, 30 days on each side. So it gets really, really hot, really, really cold. There you go. All right. Probably not a good place you want to go for a resort or anything like that. All right. Venus, of course, is the next planet. It's known as the very often as the evening star. Usually, it's the most similar to Earth. We tend to people think about Mars, but actually Venus is similar. Um, but just real quickly, this just kind of shows from Earth. Use the Sun and Mercury are so inside, close to it, that usually when the Sun has just gone below the horizon, or the Earth has turned to the Sun, that's usually when we can see Venus and or Mercury, and so that's kind of why they tend to only show up in the evenings or in the morning. Now, Venus, like I said, most similar, has a very dense atmosphere. It's made of 96% carbon dioxide. Keep in mind, we have 75% nitrogen, 18% or 18 to 20% oxygen. So there's only like a 1 or 2% of all the other gases put together. So carbon dioxide is a fairly small part of our atmosphere, but it is enormously important in Venus's. That means that, if you remember, carbon dioxide is what absorbs infrared, okay, and traps the heat in. So they have extreme greenhouse effect. It's by far the hottest planet. You think, well, Mercury would be, but actually Venus, because it can trap heat in, whereas Mercury has no atmosphere, and so it heats up, but then it also lets it all escape as well. Couple things. It does spin in the opposite, or rotates in the opposite direction as Earth does. Okay, so if you were there, you would see the sun rise in the west and set in the east. All right, and it has 243 Earth days per day, so it's very slow rotation or spin, and because of that, it doesn't have all the Coriolis effect and the winds that we talked about. So there's not a lot of change in the wind or the weather, because think about so much of our air masses that are moved by the wind. All right, so it doesn't have that, and it's has 225 days per year. Of course, keep in mind each of their days is 243 days. So very, very slow. Um, I mean, it turns around very similar to the time it takes to go all the way around the Earth. So it's like a sun. So one day, a little more than one day, actually a little less than one day. It hasn't rotated all the way around in the time that it takes to go completely around the sun. Okay, so that's kind of different than us. All right. All right, let's go on to Earth. All right. So the next thing we talk about is the Earth. Now, we're not going to spend a lot of time talking about the Earth because we've obviously been doing that. We're talking about geology, meteorology, and all this stuff that we've done so far. But a couple things. One, Earth lies within the habitable zone, and Venus is kind of on one edge, and Mars is kind of on the other edge. We're in the center. And one of the main characteristics of the habitable zone is that water can exist primarily as a liquid. Some other planets have water, but it's frozen or only as a water vapor. And basically, water as a liquid is what life as we know it allows it to happen. So, one of the most common characteristics, if you look at the Earth from outer space, is obviously the atmosphere, which is clouds and stuff, which is primarily water vapor. And you also see the blue, something called big blue marble, the blue planet, whatever. Why? Because it has three-fourths of the surface is covered by water. Okay, and that water is what allows life as we know it to exist. And those oceans are very important as a source of moisture, which allows the clouds and the rain and so forth that keeps life on land alive. It also has a lot to do with removing or adding carbon dioxide to keep it from becoming too greenhousey, like Venus, for example, extreme amounts and stuff like that. So very important stuff, but we're not going to worry about that. Now, let's talk about the moon, though. Since we have a moon, we want to talk about the moon. Uh, Uniquely about the moon is that Earth has a fairly large moon compared to the size of the planet, whereas most planets are much, 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 much larger compared to the small moons that circle around them. Okay, and so it's kind of unique. Once again, we weren't there, we don't know what happened, so scientists have come up with theories that would explain why the Earth and Moon act almost like two binary planet because they're almost similar sizes to each other. Okay, how did they come about? All right. Now, this idea of that the moon formed was called the giant and impact theory, and the theory was that at one time it was a planet nearby to Earth, and possibly a meteorite or something threw it slightly enough off course that it was pulled into Earth's gravity and collided with the Earth. Okay, which turned the Earth completely molten. It was a massive impact because it was practically the same. Much debris was spewed out, and some people think that the Earth may have rotated as quickly as every 5 hours at one time when this happened. So a very catastrophic event. Um, and then eventually the debris around the Earth coalesced into the moon. Okay, and that's why the composition they say would be very similar because basically the other planet smashed into the Earth and became all molten, and this debris was thrown out. So basically, it's made from the same material as the Earth's mantle and the core, and that's why they're so similar. And it's like I said, it's almost like a separate planet. I mean, Mercury is only about the same size as our moon, so it would kind of explain how that could have happened and how we might have ended up with these two, one's almost a planet size, smaller planet around the Earth going around. Now, because of this, the moon is only 1/6 of the Earth's gravitational pull because it's much smaller than the Earth. Because of that, it has no atmosphere, cannot hold an atmosphere around it, and because of that, when meteorites and stuff crash into it, they leave craters and so forth, and those craters are still there. Dominant effect because there is no erosion, there's no atmosphere for weather that would wash those away and things like that. And so, um, now, one of the interesting things about the moon is that we only see one side of the surface. The same side is always facing us. Okay, and basically, uh, because we are fairly large, the moon and the earth are fairly large, they exert forces on each other, gravitational forces, and it makes the moon slightly elongated. All right, and the gravitational field pulls it kind of like a needle on a compass. If you have a needle on a compass, the magnetic field of the Earth would pull it into straight. Well, when the moon is going around us, it's kind of bulged toward us because we're pulling it toward us, and so that bulge. I don't know if you can see that, but I'm just going to do it straight hand now. Okay, as it goes around the Earth's gravitational pull always pulls it back so where it faces the Earth as it goes around. And so the result of that is that every time the moon circles the earth or orbits the earth, it makes one revolution because and that means it's always facing us as we go around. And so it makes one revolution in the same time that it uh, goes around the earth. And so 29 days, something like that. All right. So because of that, we always see one side of the moon and we have never seen the other side. Now, notice there's not a dark side of the moon. The sun shines on half the moon and uh, the other half. Okay, but there is one side that we don't always see. But both sides of the moon, depending where it is compared to the sun, do get light and dark. Okay, so the dark side of the moon and the side we don't see, uh, the dark side changes, the side we see does not. All right, and it looks like we're going to stop right there, and then we will come back talk some more about moon in the next lecture.